Okay, so this is my next class, in which we are discussing about the formation of coherent sources and Newton's ring. So, what are the format? First, we have to discuss about the coherent sources. So, as per the definition of coherent sources, I have to be explain you in my previous lectures also that what are the coherent sources? Two sources are known as a coherents. Coherent if their phase difference is constant with respect to time and position. So, as you have seen in this picture there is a first two waves are coherent waves and last two waves are not coherent. Why they are coherent? Because as you have seen here that the phase of this wave is a zero and this wave is pi by as you know that this when waves are started from the starting point their phase is zero and this is the here their phase is known as a pi by 2 and here their phase at this point their phase is pi. Okay, so this wave is started from lower end, so we can say that this the phase of the below wave is 2 pi. So if I'm going to check the phase difference, the first wave having a zero phase, another wave having a pi by 2 phase. So what is the phase difference? Phase difference is pi by 2. Okay, now uh, this is pi, so 0 and pi, the phase difference is pi. Okay, okay. So here we can I'm going to erase it first. So this is this one the this phase is pi and next phase is this phase is 0. So 0 minus pi is pi. Okay, right? Now, after pi, what is the phase? What is the phase here? Here, the phase is 3 pi by 2. Okay. So, now we are going to subtract this phase to this lower one, wave phase. So, what we will get? Pi by 2 minus 3 pi by 2 is again pi. And what is the phase here? This is 2 pi. Okay, and what is the phase of first wave? First wave phase is pi, second wave phase is 2 pi. So if we are getting the if we are subtracting 2 pi from the pi, then what we get again pi. So we have seen here that each and every time the phase difference between these two waves are pi. So we can say that this first wave is coherent with the second wave. But if we are going here, then we can check here that the phase of this first wave is pi by 2 and here phase is we can say that this phase is pi. So if we are taking a phase difference, the total phase difference is pi by 2. Okay, but if we are going here, the phase is pi. Okay, but if we are taking a phase difference between these two waves, then we don't know the way phase of this point because we know the peak value of the phase difference, but after that we cannot know the exact value of the wave until and unless the wave phase is not written over here. So if we are going to subtract a pi, but if we are thinking that it is pi, then it is maybe 3 pi by 2. So, and it is more than 3 pi by 2. And if we are taking the phase difference between 3 pi by 2 and pi, then we are not getting a phase difference pi by 2 exactly. It is more than pi by 2. So, here the phase difference is going to be a change. And in the same way, if we are calculating the phase difference between this wave and this lower wave, then we are getting the different phase difference at different time. So we can say that the first two waves are coherent and last two waves are incoherent. Right. So what are the coherent right now? I think so it is clear to all of you. The two waves are coherent if their phase difference is constant with respect to time and position. Now, it is impossible to create coherent sources by two sources, because each and every sources are generating waves in a different time intervals. That's why two very highly monochromatic sources are also not behave like a coherent sources. So we can produce coherent sources by two methods. First method is by the division of wavefront. So how we can produce by the division of wavefront? So for division of wavefront, what we are doing, we are passing as the Youngs did. They make two pinholes in a cardboard sheet, and then a wave front is incident on it. When wave front is striking on these two pinhole sources, and by the Huygens wave theory, we know that every point of the wavefront is vibrating on a same phase. So, and they are also capable to produce new um, light source. So each and every point is capable to produce new light source, as well as they are vibrating on a same phase. So they produce the same phase waves from these 2 points. In this way we can produce same waves from these 2 points, and when these two waves are interferes to each other, they form bright and dark fringes. So in this way, what we are doing, we divide wavefront into a two small wavefront, and we produce two coherent sources. So this method is known as a this method is basically used for production of coherent sources by the division of wavefront. Now we are moving towards the next technique. The next technique is known as by the division of intensity. So, for intensity, we need a thin film. So, what is this thin film interference? Thin film interference occurs when light waves reflected from the top and bottom surface of a thin layer whose thickness is similar to the wavelength of the light. It means that you have seen many times the soap bubble, and different light patterns form over the oil when oil is split over some wetty surface. Then we have seen number of different types of light patterns over it. So this is formed because of the thin film interference. So whenever the soap bubble is formed, there is there is a thin film or there is a thin film consists between the air film. One side there is air, another side is air, and in between that there is a soap film consisted. And this soap film is known as a thin film. Similarly, when we are talking about the uh, water that oil flame, then there is a surface on which we see that there is a water, and over that oil is splitting out, after that there is a air. So between air and water, the oil thin film is consist. Similarly, now see here, thin films are two type. One is a as you see here, there is a this type of a thin film when two layers are parallel to each other, then this type of a thin films are known as a parallel thin film. And if the two surfaces are inclined at some angle, this type of a thin film is known as a wave-shaped thin film. So how two coherent sources are formed with the help of thin film? As you have seen here, if a light ray incident on a point A, then the few amount of the light is reflected from here, and few amount of the light is transmitted from a point. As we know that whenever light is incident on any point, the less intensity on any transparent medium, not at a obstacle or some translucent medium. When a light is incident on a transparent medium, at that time, minimum energy is reflected and maximum energy of the light is transmitted. So transmitted light consists with the 98% of the intensity, and reflected light is consist by the 2% of the intensity. When this transmitted light reaches at the second surface of the thin film at B point, the same thing is going on here. A few amount of the light is transmitted and few amount of the light is reflected. So 96% of the light is transmitted, and very less means nearly about 2% of the light is reflected back. Now this reflected light, which I depict here by the red line, when it's strike over the C point, here it again transmitted and reflected. But as we know that the reflected light consists with the high amount of the energy, so the reflected beam having 1.98% energy, and now because maximum energy is transmitted, only the few amount of the energy is reflected. So it's nearly equal to the zero. So reflected energy is nearly equal to the zero now. Now, so reflected light having 2% of the energy, and transmitted light having 1.98% of the intensity. So 2% intensity and 1.98% intensity is nearly equal. Therefore, we can say that these two lights are capable to produce a interference pattern, because they both are produced by the same light source and they are vibrating on a same frequency. So they are making two coherent source. One coherent source is produced by that wave which is coming from the reflecting from the A point, and another which is reflecting from the C point, and both are having a same amplitude. Okay, so in this way, the two coherent sources are produced due to the division of intensity. We have seen here the intensity is divided. Okay, now same thing is happen in the wave shape film. You have seen that whenever a light is incident over here, the few part amount is reflected and maximum part is transmitted. When it's strike at a lower point, the maximum point is again a few amount is reflected and it's travel at outside. Then these two waves are interfered to each other and produce the interference pattern. So in our course there is okay, so because in our course the both the applications are depending upon the division of intensity or thin film interference, so that we have to be know here the path difference between these two waves, which is reflecting from the first surface and which is reflecting from the second surface. Okay, so what is the phase path difference between these two waves? The path difference between two waves are 2 mu t cos r plus minus lambda by 2 for the parallel thin film, and for the wave shape thin film, the path difference is 2 mu t cos theta plus minus r plus minus lambda by 2. Okay, so what is mu here? Mu is the refractive index of this medium. R is the angle of refraction. Okay, so angle, as you know that where is the angle of refraction? So here, if we draw a perpendicular, then this is the angle of refraction R. And what is mu? Mu is a refractive index of this medium. Okay, lambda is the wavelength of its incident light. Okay, now here and T is the thickness of thin film. Okay, so this is the path difference between this first wave which is refracting from the upper surface of the thin film, and second wave which is coming from the after the refraction from the second surface of the thin film. Okay, so this is the path difference for wave shape film. So as you know, wave shape film is consistent two way two surfaces are inclined by some angle, and suppose that this angle is a theta. So in this part difference, theta is the angle of inclination, and again what is mu? Mu is a refractive index of the thin film, and what is r? Again r is a angle of refraction, which is here. Okay, and after refraction the wave go here, so we are finding the path difference between the wave ray which is refracting from the first surface, and after transmit refracting from the surface and transmitting from the first surface, we are going to find out the path difference between this wave and this wave. So what is the path difference? Delta 2 mu t r 2 mu t cos theta plus minus r lambda by 2. Okay, now this you have seen here there is some extra part difference which I add and separate here. It is equivalent to pi by 2. This has come due to the Stokes law. What is the Stokes law? So I have to explain it here. Whenever the light ray is incident coming from the rarer medium and incident on some denser medium, then after the refraction their phase is changed. As you see here, the light is coming by the downward phase, but when it is reflecting, it is going by the upward phase. It means that total one pi phase is changed, means 180-degree phase is same. So in that condition, how much part difference is generated? Part difference is generated it equal to pi by lambda by 2, because as we know that there is a relationship between phase difference and path difference. So what is the relationship between the phase difference and path difference? Phase difference is equal to 2 pi by lambda multiply by path difference. Okay. So with the help of this formula, if the phase going to be changed by the pi, so pi is cancelled by the pi. So how much part difference is left? Lambda by 2 part difference is left. So whenever there is a phase difference of pi, the part difference of lambda by 2 is generated in the part difference. So this part difference is generated due to the Stokes law, Murtaugh law. But in this way, this part difference is not generated. Why? Because now the wave is transmitted to the denser medium and reflected from the denser medium. So as you see here, it is coming from the downward phase and reflected also by the downward phase. So Stokes law says that when a light ray is incident on a denser medium and coming from the rarer medium, whenever it is reflected from the denser medium, it's phase the path difference of lambda by 2. Either it can be subtracted from the path or it can be it will be a additional in it. Okay, so this is all about the formation of coherent source and thin film interference. Now the main next topic which I am going to be deal, it is a Newton's ring. It is a very important topic. So what is the Newton's ring? Basically Newton's rings are basically interference patterns which is formed due to the thin film interference. Okay, so how we get this Newton's rings? So when we placed a plano-convex lens of large radius of curvature on a glass slab, then around the point of contact, as you see here, this is the suppose this is a glass slab and this one is a plano-convex lens. So this is the point of contact text. So around this point of contact, you have seen that a way-shaped thin film is consistent. So way-shaped thin film is consistent, and its thickness is gradually now increases. And now if we incident a monochromatic light, so if we incident a monochromatic light on this normally, then around this point of contact, concentric dark and bright fringes appears, which are known as Newton's ring. So I think so the definition of Newton's ring is clear to all of you. So how Newton's ring looking like, we will discuss in our next slide. Here we are discussing the formation of Newton's ring by the ray theory. So suppose there is a one glass plate and I have placed a plano convex lens on it. So around the point of contact, you have seen here the thin film is consistent. You can imagine a bowl is placed over over some plane surface. So whenever we placed a bowl over a plane surface, you have seen that around the point of contact means that around the point of contact in a 3D view, if you have seen that, then a spaces is created, a way-shaped passage is created. So similar type of passage is created around the this point when we placed a glass plano convex lens on a glass plate. Okay, so right now we are not incident monochromatic light normally over it. We are a incident at some angle. After that, I can explain by the normal incident. So suppose that there is a one light which is incident normally on it. You have seen that this is blue color light. Now it is incident at some angle on the plano convex lens. Okay, on a upper surface of plano convex lens at some angles, at some angle. Okay, now this light is after incident over this point, light is transmitted to the plano convex lens and reflected from this point. As you see that this point is the upper surface of the thin film. In our previous lecture, in my previous slide I have explained this is the wave shape film. Now here we incident a light and this is the upper surface of the wave shape film. So light is reflected from this point. So similar thing is happen over here. This here the film is consists between the lower surface of the plano convex lens and the l- upper surface of the glass slab. So between here somewhere the thin film is consistent, and if light is incident on it, then the first reflection occur at this point, which is the lower surface of plano convex lens. Okay, but a few amount of the and after that it's transmitted from the plano convex lens, and few amount of the light is transmitted uh, towards the a glass slab. Now when it incident on this area at this area, from this is the lower surface of the thin film. What is this? This is the lower surface of the thin film. And now uh, I can explain is here also. So this light is now reflected back and coming here. Now this next part, few amount of the light is transmitted and strike at lower surface. So where is the lower surface? Lower surface is here. Yeah. Now it is also reflect back from this point and rejected out. Okay, so this thing I have explained during my thin film interference. So similar things happen here. Now light is incident over here, and after the reflection, that after the reflection, light transmitted to the plano convex lens and reaches out. Now the interference occurs between this yellow color light and this blue color light, because the yellow color light come from the upper surface of the thin film and the blue color light is coming from the lower surface of the thin film. And if somebody see from this side, then they can find some interference pattern over here. Okay, now similar thing I am going to explain by the monochromatic light and for normal incident. I think so with the help of this explanation you can easily know the normal incident. So whenever the light is incident, suppose normally lay on plano convex lens, it's going to the lower upper surface of the plano convex lens and reflect back to the same point. As we know that whenever light is coming from the normal, it reflect back to the, I mean, it follow the same path. Okay, after a few amount of the light is transmitted downwards towards the glass slab and strike over here, and again it's reflected back. When it's strike on this point, again it's reflected back and meet with the first blue light which is reflected from this point, or the orange light which is reflected from the upper surface. So upper surface is light and lower surface is light, both are now meet with each other, and they can create a interference pattern over here. If their path difference is equal to n lambda, then we find a bright fringe over here. And if its path difference is 2n plus 1 lambda by 2, then we got a dark spot over here. Okay. Now in this way, there are n number of lights are striking, and n number of points we can see around this whole thin film, or around this whole point of contact, right? And as you see, if all over, if we can see same point over here bright, or here bright, and this way, if you are joining this all point, then we can see a circular pattern around the point of contact, and these circular patterns are basically a Newton rings. Okay, so I think so it's clear to you. Now I'm going to explain the experimental setup of Newton's ring. So for the experimental setup, as we know that we need a monochromatic light source. So suppose that we are having a monochromatic light source. In front of that, we can place lenses for the proper focusing of the light, and at the 90 and we can place our assembly means the combination of glass plate and convex lens at a 90-degree with monochromatic light source. And this is the glass plate and panoconvex lens of radius, and then we incline a 45-degree glass plate with respect to a monochromatic light source, and this glass, and over it we can place a traveling microscope. Okay, so this is the experimental setup from Newton. Why we are placing this glass plate at 45-degree? Because we have to be see the pattern at 90-degree, as well as we have to be incident light at 90-degree. So this 45-degree inclined glass plate help us to make a 90-degree angle of light over this plano-convex lens and glass plate, because monochromatic source is placed at a 90-degree from the this assembly. So if we are if we want light at 90-degree, if we want to incident a light at 90-degree over this assembly, so we need to place this, then this glass plate help us to make this angle. Okay, so how it's work? When light source, we glow the light source, or we start the light source, rays coming towards the lens, and after that this light ray incident over the glass plate. Now this glass plates, because this glass plates is inclined at a 45-degree, they transmitted light at the angle of 90-degree towards the plano-convex lens, or we can say the reflected light at 90-degree towards the plano-convex lens and glass plate assembly. Okay, when this light is now the light is incident normally over this assembly, and reflect black from the few on the, as we know that the first the reflection take place from the upper surface of the thin film, which is actually the lower surface of plano-convex lens. So light is reflect back from the upper surface of the thin film, and rest of the amount of light is uh, transmitted towards the glass plate, and again reflection take place from this point, and light is reflected towards the glass plate. Now this yellow color light is reflected from the upper surface of the thin film, and blue color light is reflected from the lower surface of the light. So we get two reflected light beam. One is a blue color light beam, another one is a yellow color light beam. Now these two light beams travels towards the microscope, traveling microscope, and they both are now interfere to each other, and they form such type of a patterns which are known as a Newton's ring. So you have seen here, these are the concentric dark and bright rings which are known as a Newton's ring, and this pattern you have seen over here around the point of contact. I think so. This topic is clear now. What is the Newton's ring, and how the Newton's ring we can this how we can form Newton's ring in our laboratories. Okay. Now in our next topic, we are calculating the radius of a Newton's ring. So, for that, before calculating the radius of the Newton's ring, we have to do some suppositions and find out the part difference and other thing. So we will discuss this in our next lecture. Thank you very much. We will meet in our next lecture.